Good morning, distinguished colleagues, ladies and gentlemen. Today I will talk about a concept that we introduced only a few years ago, 6D printing, and how it opens the door to a new level of programmability, adaptability, and intelligence in additively manufactured structures. In this presentation, I will walk you through the scientific foundation of 6D printing, the role of smart materials and multi-axis deposition, how multi-scale modeling and AI can make structures truly adaptive, and demonstrative examples where we observe superior performance compared to previous methods. Our vision is to bridge manufacturing with intelligence, to create structures that are not only fabricated, but that behave, adapt, and learn. Thank you once again for being here. Let's begin. To understand why 6D printing is needed, we have to look at the evolution and the limitations of the technologies we already know. 3D printing gave us geometric freedom, but the structures are static, anisotropic, and often wasteful because of support materials. Most importantly, there is no way to embed behavior or responsiveness into a 3D printed object. 4D printing attempted to change that. By using smart materials, structures can morph over time in response to heat, moisture, light, or other stimuli. But the problem remains. The response is constrained by planar layer deposition. The morphing is slow, limited, and fundamentally restricted by 3-axis printing process. 5D printing introduced multi-axis fabrication. This brought curved layers, better mechanical strength, and reduced material usage. However, these parts are still passive, strong, but unable to sense or to adapt. There is geometry, but no intelligence. So the challenge is clear. None of these paradigms, 3D, 4D, or 5D, can simultaneously combine geometric freedom, smart material integration, and fully programmable behavior. This gap is exactly what motivates the shift toward 6D printing. Today's AM can produce complex shapes, but it cannot deliver structures that autonomously adapt, evolve, or reconfigure themselves. That is the fundamental limitation, and this is exactly where 6D printing introduces a paradigm shift. Tomorrow's structures must be far more than static components. They must be able to sense their environment, respond to external stimuli, adapt their behavior, repair themselves, and in some cases even learn from repeated interactions. These requirements are emerging across aerospace, robotics, biomedical implants, soft machines, and infrastructure. To achieve this, AM must progress from single shape making to behavior programming. In other words, we are no longer designing only geometry. We are designing how a structure will behave throughout its lifetime. The roadmap you see on the right captures this journey. In the short term, we validate multi-axis printing integrated with smart responsive materials. In the medium term, these systems become fully functional adaptive components tested in realistic industrial environments. And in the long term, we envision widespread commercial adoption where adaptive, intelligent products become mainstream. This entire vision, structures that are shaped, activated, and programmed at the moment of fabrication, is the essence of 6D printing. Now let's define exactly what we mean by 6D printing. 6D printing is a manufacturing paradigm that merges three capabilities: multi-axis fabrication from 5D printing, stimuli-responsive smart materials from 4D printing, and the content of programmable behavior directly into the printed structure. In practice, this means that we are no longer just depositing material, we are depositing function. We control the geometry with curve layer, orientation control printing. We control the material through smart polymers, composites, and multi-material combinations. And we control behavior by designing how the structure responds over time to heat, stress, magnetic fields, or other stimuli. So the question is, what exactly is the sixth dimension? It's not an extra spatial axis, and it's not time. The sixth dimension is intelligence. the ability of a structure to adapt, evolve, or reconfigure based on encoded behavior. Behavior is no longer an afterthought. It is printed into the object itself through its material composition, its internal architecture, and its toolpath-driven orientation. To understand how 6D printing works, we need to look at its scientific foundations and the workflow that connects them. Everything begins with smart materials, polymers and composites that respond to external stimuli such as heat, pH, mechanical stress, electricity, or magnetic fields. These materials provide the intelligence layer that allows structures to move, morph, or change properties after fabrication. Next, we enhance these materials with nano-reinforcements. Nanoparticles, nanoribbons, and nanosheets greatly improve strength and multifunctionality. They also allow us to fine-tune the response, for example, faster actuation, stronger burning, or increased sensitivity to a specific stimulus. The third foundation is behavior encoding through deposition paths. Because 6D printing uses multi-axis deposition, we can orient fibers in smart domains along any direction, not just flat layers. This curved layer orientation controlled printing effectively tells the structure how to act when stimulated. The workflow on the right summarizes the full process. We start with smart structure requirements, perform mathematical and multi-scale modeling, identify an interaction mechanism, and define the initial geometry. Then, through optimization, we determine the right multi-axis toolpaths, apply 5D printing, and finally evaluate the static and dynamic behavior under stimuli. The result is an efficient smart structure, first statically and ultimately dynamically capable of precisely controlled actuation and adaptation. 6D printing is powerful because it integrates two forms of intelligence, process intelligence and material intelligence. And it's the combination of these two that enables truly programmable structures. On the process side, multi-axis deposition gives us unprecedented control of filament orientation. We can align extrusion paths with stress trajectories, which significantly improves mechanical performance compared to planar layering. This also means we can locally tune stiffness, actuation direction, and response speed simply by adjusting the orientation of the toolpath. Another major benefit is the reduction of support material. Because we can print on curved surfaces and in multiple orientations, we eliminate many of the support structures required in 3D printing, leading to 30 to 5% material saving and faster fabrication. On the material side, we integrate smart materials such as PL-ATP UV layers, hydrogels, safe memory polymers, and advanced nanocomposites. Nanofillers such as carbon nanotubes, graphene, or iron particle system amplify the actuation force sensitivity and overall functional response of the printed part. When we combine these materials with curved layer deposition, the interface geometry governs how the structure morphs. The intensity of bending, the direction of actuation, and the degree of programmability become controllable design parameters. To illustrate the impact of 6D printing, let me show you two representative case studies. On the left, we compare classic 4D printing with our 6D approach under identical head stimulation. Both examples are made of the same materials, but their deposition logic is different. In 4D printing, the layers are horizontal, which limits the bending intensity and controllability. In contrast, 6D printing used inclined V-type curve layering. The orientation allows the structure to bend more strongly and more predictably when heated. So simply by changing the deposition geometry without changing the material, we achieve significantly enhanced morphing performance. On the right, we see a magnetic field responsive structure. Here, inclined multi-material layers contain magnetic nanoparticles embedded within a polymer matrix. Without a magnetic field, the structure remains static, but when a field is applied, the nanoparticles align and interact with the curved layer geometry, producing large directional deformation. Again, the key is the synergy between the smart materials and toolpath orientation. These two examples show that 6D printing does not rely on exotic materials alone. The intelligence emerges the combination of smart materials and multi-axis deposition. The result is highly tunable, functional, and adaptive structure that previous AM paradigms simply cannot produce. Up to now, we've discussed how 6D printing allows us to embed smart behavior through our multi-axis toolpaths and smart materials, but the real transformation happens when we bring AI into the loop. On the left, you see the evolutionary design loop. We begin with a pre-programmed shape and material selection, but then we stimulate how that structure behaves under different stimuli. The data generated from these simulations, combined with the real measurements from printed prototypes, feeds back into AI and machine learning models. These models learn which path geometries, materials, and interfaces produce the best functional results. This creates a continuous cycle: design, simulate, print, observe, learn, redesign. Each iteration improves the next generation of smart structures. On the right, we extend this into a full AI-driven digital platform. Here we combine material databases, slicing criteria, machine settings, physics-based models, and digital twins. Sensors inside the printer and inside the final structure continuously generate data. AI processes this data, predicts outcomes, and adjusts parameters either during printing or during operation. In other words, AI transforms 6D printing from a predefined manufacturing process into a learning ecosystem. Paths evolve, behaviors adapt, and the system becomes smarter with every printed part. 6D printing is not just an incremental improvement in additive manufacturing. It unlocks entirely new application domains across multiple industries. Let me highlight a few examples. In the biomedical sector, 6D printing enables adaptive implants and medical devices that can reshape or respond to physiological stimuli. We are talking about orthopedic implants that match patient curvature and change stiffness during healing, vascular grafts or stents that react to pressure or biochemical cues, and prosthetic interfaces that dynamically adjust to a patient's anatomy and improve comfort and function. In aerospace, the potential is equally transformative. We can produce morphing wing components that bend under aerodynamic loads and return to their original shape, deployable or reconfigurable satellite structures with embedded actuation and smart vibration dampers that tune the stiffness in real time to protect sensitive equipment. Finally, in civil and infrastructure applications, 6D printing enables structures with built-in resilience and adaptability. For example, self-healing joints that respond to stress signals, dynamic facade elements that reconfigure based on climate or sunlight, and intelligent pavement sensors that change stiffness under load and provide real-time information about traffic or structural health. Across all these domains, the ability to print both geometry and behavior at the same time is what fundamentally differentiates 6D printing and gives it such broad disruptive potential. At this point, the question is not just what 6D printing is, but why it is fundamentally disruptive compared to 3D, 4D, and 5D printing. First, structural strength can increase by up to a factor of 3. This comes from curved, stress-aligning toolpaths that follow real load trajectories, something traditional planar printing cannot achieve. Second, the stimulus responsive speed improves dramatically. Because we can orient material domains in 3D space, actuation becomes 2 to 4 times faster, whether it's thermal, mechanical, electrical, or magnetic. Third, 6D printing is far more material efficient. Multi-axis deposition reduces the need for supportive structures, saving 30 to 50% of material while also improving surface quality. This naturally leads to waste reduction. We see reductions of 50 or 70% of unnecessary filament use, support material, and post-processing. Fifth, multifunctionality increases. With 6D printing, we move from single-function components to structures with 2, 3, or more integrated functions, such as sensing, actuation, stiffness tuning, and even self-healing. And finally, programmability. This is the true disruptor. Behavior is not added afterward, it is encoded directly into the deposition paths and the smart material architecture. Let's look at the long-term vision enabled by 6D printing and intelligent adaptive manufacturing ecosystems. The first pillar is fully autonomous adaptive structures. These are structures that do not just respond once, but continuously self-adjust throughout their lifetime, adapting to load, temperature, damage, or environmental change. Second, 6D printing aligns naturally with zero-waste circular manufacturing. With multi-axis deposition, material-efficient designs, and integrated sensing, we can create closed-loop material flows and reduce environmental impact across the entire life cycle. Third, we move toward materials that involve and learn from use. Through embedded sensing and AI-driven feedback, the behavior of the structure is refined over time, creating adaptive materials that improve with experience. Fourth, this vision transforms biomedical engineering. Imagine passing specific implants, processes, and scaffolds that not only fit perfectly but also adapt in real time to physiological changes, becoming part of a dynamic interaction between the human body and the printed device. Together, these pillars define a future where engineering systems are intelligent, sustainable, and capable of self-evolution. 6D printing lays the foundation for this future, a new generation of smart adaptive structures across all engineering domains. Although 6D printing opens a new frontier, several key challenges remain before it can reach full industrial maturity. The first challenge is material process compatibility. Smart materials such as SMPs, hydrogels, and nanocomposites must be processed reliably using multi-axis deposition. This requires controlling melt behavior, viscosity, nano-reinforcement dispersion, and ensuring that the material stimulus response functionality is preserved throughout printing. The second major challenge is standardization and certification. Because 6D printing structure can change geometry, stiffness, or function over time, traditional certification frameworks no longer apply. We need new standards for safety during actuation, long-term stability, durability under repeated stimuli, and for approving adaptive components in aerospace, biomedical, and civil applications. Addressing these challenges is essential to move 6D printing from laboratory demonstration to large-scale real-world deployment. Another key challenge for 6D printing is the need for accurate multi-scale simulation and predictive design. Because behavior is encoded during printing, we must understand what happens from the molecular level, polymer chains, and nanofilters up to the structural level under real stimuli. This requires molecular dynamics models, finite element simulations, and coupled multi-scale frameworks that link nano, micro, macro behavior. These predictive tools are essential to design optimized behavior encoded toolpaths. A second major frontier is integrating sensing intelligence and actuation directly into the printed part. Future work focuses on in-situ sensing during printing, embedding conductive or magnetic domains, linking structures with digital twins for real-time learning, and ultimately fabricating material intelligence in a single, unified process. To conclude, 6D printing represents a fundamentally new design ontology, one where geometry, material, and behavior are programmed together from the very beginning. By unifying multi-axis curved layer fabrication with smart materials and behavior encoded directly in the toolpath, 6D printing introduces a completely new design language. This new paradigm bridges manufacturing with intelligence. Unlike 3D and 4D printing, which remain limited by planar layers and predetermined responses, 6D printing fully integrates AI-assisted modeling, multi-scale simulation, and digital twin feedback loops. This connection between fabrication, sensing, and real-time adaptation is what makes the technology transformative. The outcome is a new class of adaptive high-performance structures. Stress-aligning curved toolpaths produce stronger and more responsive parts. Multi-material interfaces and embedded smart domains enable fast and accurate morphing, and the reduction in support structures improve both material efficiency and sustainability. These capabilities have already been validated through early case studies, including thermally activated bending and magnetically driven actuation, and they point toward a future where structures are not just made, but intelligent, adaptable, and self-evolving. Thank you for your attention. Have a wonderful day.